And then the two types of supernova that you answer tonight. There's the 1A, which is C above, and actually I added 2 above. So that, of course, is your red giant who's dumping on your retired star, but the material gets dumped on the white dwarf, and it's almost near that Chandrasekhar limit, and then actually the star, the white dwarf, comes alive again with nuclear fusion, and it just cannot handle that, and it blows itself up. Sad face. And gravitational redshift, I brought in a figure from your textbook down here in the, sorry, not quite. So the type 2 supernova is the explosive end of a massive star. And I went ahead, and I don't think you need to know these details, but we talked about this before. It was like on your last test that basically silicon has fused to form iron in the core, and iron can't fuse. So now gravitational redshift. I have a little thing down there. And I say that basically that little orb there is either, your book says, think of it as a neutron star or a white dwarf. And it causes a dent in the fabric of space and time. And so in order the closer that light gets to it, in order for that young lady who's far too close to that neutron star or the white dwarf to see it, in order for that light to get to that woman from the lamp, it has to climb out of kind of a gravity well. And so it loses energy. So the light loses energy as it's climbing out. Then something light. The 3 outcomes of Einstein's general theory of relativity with regard to length. Your length will become shorter. Time will unfold more slowly. And your mass will increase the faster you go. That is actually, you won't notice it, but somebody who is not moving, if their frame of reference, will see that effect on you. So then black holes, I drew a little diagram there. That's singularity in the center. There's my event horizon. And then, of course, that radius is this Schwarzschild radius. And then in orange there, kind of it is an afterthought, when we talk about escape velocity, to me, you have to kind of look at the event horizon. So it says if you're within the event horizon, you would need to go faster than, hopefully, c is the speed of light to escape. So to the next chapter. The first one, of course, this chapter's on the Milky Way. So 2 things about the Milky Way I have in red and purple up there. The red is kind of the general anatomy of the Milky Way, and actually general anatomy of any good spiral galaxy. We have the disk component, the central bulge or the nuclear bulge, the halo region, and globular clusters outside in the halo region. And then the purple kind of highlights some dimensions of the Milky Way. It's about 1,000 light years side to side in diameter. Then out to the edge there, it's about 1,000 light years. And then we are about 27,000 light years from the center. And then I brought in a picture for the next one. Objects need to stay in orbit about that supermassive black hole in the center of our galaxy, because if they don't, we'll be one big blob. So kind of that bottom picture there, the yellow path is actually the orderly disk stars. We're a disk star. And then kind of the green trajectories are what halo stars do, how they orbit the central bulge. And then the next one, I don't know if you recognize those kind of strips. There's 7 strips, and the 4th strip down is actually what the Milky Way looks in visible light. The other strips are different wavelengths. And the point there, and I didn't emphasize it this semester in lecture, but the reason we need to look at the Milky Way in different wavelengths like that is so we can see through the dust. Actually, those looking at different wavelengths kind of tease out different features, because different wavelengths can come through the dust, not visible light. The next one, I brought in a figure 2. So that figure down there is really kind of dark, but what you're looking at is kind of the disk of our galaxy and those red lines are trying to kind of highlight things. The top red lines are actually talking about halo stars, and the bottom red lines are talking about disk stars. And we said that halo stars are older stars, and actually halo stars tend to be in red over there, metal poor. And disk stars are kind of an assortment, but kind of younger stars, and they tend to have more metals. Then actually related to that is this idea of older and younger, is population 2 and population 1. Population 2 seems like it should be kind of the latest generation, but population 2 we say is the oldest stars, and they're located again in the halo, and then population 1 actually are the younger stars, and they're in the disk. And Sagittarius A star is the black hole in the center of the Milky Way. And then in orange here, I don't think you necessarily need to know this, but you're probably familiar with Sagittarius as a constellation. And the reason we call it Sagittarius A star is actually we have to look in the constellation Sagittarius to find this. So, and then instead of whole, that first word should be how. So how do we know there's a black hole in the center of our galaxy? And again, like we look at other galaxies about stars moving. And so we looked at the motion of stars in our own galaxy, and in blue it says we came up with the fact that, or I guess in green it says we came up with the mass of that object is 4 million solar masses. So the fact that there's that mass in the center of our galaxy, and we know how big that mass is confined to, that density must mean it's a black hole. And then for the last chapter, I went ahead and broke it up onto 2. So this is the first page of 2. And I know why students are thinking sometimes the irregular is the third type of galaxy, but because I think that's what your textbook talks about. But I really like it. The 3 types of galaxies are spirals, barred spirals, and ellipticals, kind of back to Hubble's tuning fork diagram. And then we talked about the nuclear bulge and the winding of the arms. So basically, the more tightly wound the spiral arms, the larger the nuclear bulge. And then in 1920s, that was finally when we figured out the concept of a galaxy. And so Edwin Hubble used Cepheid variables to see how far away the Andromeda nebula/galaxy was. I just think that's funny. So he watched that Cepheid variable, okay, and he related how it pulsed, okay, back to its luminosity, the standard candle. And then the next one, as we look at different galaxies at different distances from us, if a galaxy is, well, since it takes light a certain amount of time to get to us, the light we see left a long time ago, when the galaxy was younger. And the last one up there, standard candles. This is kind of wordy. I might change it a little bit in the final review page. But standard candles we talked about today. Cepheid variables are kind of standard candle. Main sequence stars are standard candle. But basically we know the luminosity. We know how luminous certain objects are. And then in green I said we can compare what they look like, or their brightness, with their known luminosity to get to distance. I guess that's not too bad. Okay. And then the last page, Hubble's law, says the more distant the galaxy is from us, the faster it's moving from us. And then there's kind of his little plot where we have the scatter plot, the distance of the galaxy along the x-axis, and that's supposed to say recessional v for recessional velocity along the y-axis. And we can estimate the age of the universe, and I think all you need to know is the range, 13 to 15 billion years old. And actually there's other ways to estimate the age of the universe. That's one way. So we've said as something recedes or moves away from us, thus recessional motion, we said it can have a red shift. And so that actually happens with galaxies that are moving from us. So with the increased distance from us, the faster their motion and the faster their redshift. So this redshift increases with distance. All right. So kind of back to the idea of the farther away we look at something, the older, the more of a baby picture it is. So we can actually kind of see how galaxies change over time by comparing the distance ones with the closer ones. Look for baby galaxies far away, more mature galaxies closer, and kind of fill in the blanks for evolution of galaxies. The protogalactic cloud, that actually is just beginnings of a disk, or could be a spheroidal, but beginnings of a galaxy. And the next term, it's just simply saying stuff was closer together early on, so galaxies were more likely to run into each other or interact. The next two terms go together, and I think I actually start with quasars. So quasars basically is that the black hole that's in the center of the galaxy is feeding, and can be very energetic out the kind of the center, perpendicular to the disk. So if we say a galaxy is active, then the black hole must be feeding. And that's all I got. See, that review session only took less than 20 minutes. So I got you down for 10 and 10.